Welcome back, everyone. Man, I hope you all enjoyed that little Solana Cloud Fundamentals vacation because it's time to get back into the garage. On behalf of Forge College, I'm absolutely thrilled to guide you through today's explainer. We're going to roll up our sleeves, grab our diagnostic tools, and really look under the hood of the Ethereum virtual machine. Today, we're focusing on a topic that truly separates the weekend tinkers from the hardcore Web3 engineers. We're analyzing opcode efficiency. Let's get right into it.
Okay, so let's start with a question that has probably kept you up at night at least once. Have you ever wondered why a seemingly innocent, tiny little line of Solidity code suddenly acts like a gas-guzzling V8 engine the second you compile it? You write this elegant little loop, you deploy the thing, and suddenly it's just draining your ETH like there's a giant hole in the gas tank. Well, the reason is that high-level code can be incredibly deceptive. What looks super cheap in Solidity might actually be triggering massive heavy machinery down at the bare metal EVM level.
Here's our blueprint for today's masterclass in engine tuning. We'll be hitting opcode efficiency, EVM cost drivers, spotting guzzlers, doing a full code teardown, and finally wrapping up with the optimization loop. We aren't just guessing today, we're measuring.
All right, section 1, opcode efficiency, the core concept.
So what exactly is opcode efficiency? It's basically the practice of mapping small source code patterns to the concrete EVM opcodes they compile into, and then reasoning about their gas weight. Think of it like this. Real optimization isn't about guessing. It's definitely not about relying on vague heuristic rules of thumb. It's about tracing your high-level code all the way down to those bare metal gears and pistons to find the heavy hitters. You really have to treat the high-level pattern, the compiler's emitted opcode sequence, and the actual gas cost as three separate explicit layers.
Let's turn to section 2, EVM cost drivers. Time to map out those costs. Now, take a really good look at this component manifest because honestly, this is your ultimate cheat sheet for EVM mechanics. Notice the massive disparities here. Things like MSTORE and MLOAD, your basic memory operations, and push operations are incredibly cheap. We're talking down around just 3 gas. But look up at the top of the list. SLOAD, which is reading from persistent storage, whacks you for 800 gas every single time you use it. And in SSTORE, writing to that persistent storage, ouch, that starts at 5,000 gas and only goes up from there. Seriously, a single SSTORE is like replacing the whole transmission on a car. And then you've got call sitting at 700 plus gas, which brings its own external overhead and reentrancy headaches.
But listen, understanding the per opcode cost is essential, sure, but it is not sufficient. You also have to reason about multiplicative effects. You need to be very, very careful with memory expansion. Memory expansion gas is strictly non-linear. It starts off incredibly cheap, just those 3 gas M stores. But as you expand into new 32-byte word boundaries, the gas costs balloon quadratically. If you aren't careful with temporary buffers or dynamic byte operations, you'll suddenly see your gas costs compounding so rapidly out of nowhere it'll completely blindside you.
Which brings us to section 3, spotting guzzlers, finding out exactly where your gas bleeds.
If you're playing detective, these are the 3 biggest gas thieves hiding in your compiled bytecode. First up, repeated storage reads in view functions. A developer might read the exact same storage slot multiple times in a single computation, emitting multiple 800 gas SLOAD opcodes. Yikes. Second, naive loops with persistent storage writes. If you carelessly drop an SSTORE inside a loop, you are multiplying a massive 5,000 gas operation by your iteration count. Literally a fortune in gas. And third, unexpected memory expansion from dynamic buffers. When helper functions concatenate or allocate blindly, they trigger those brutal quadratic memory expansion penalties we literally just talked about.
All right, section 4, code teardown. Let's put some code on the lift and strip it down to the chassis. Imagine a simple view function that's just doing some everyday math. In the original code, it reads a storage variable, let's call it important value, 3 separate times across different expressions, to calculate a return value. Because the compiler needs that slot value at specific compile time ordering points, it just blindly emits 3 separate SLOAD opcodes. Now look at the refactored side. This refactored code smartly caches important value exactly once into a local memory variable. Let's call it V. Then every subsequent math operation just references V instead. This side-by-side comparison reveals the absolute true power of opcode efficiency. That simple one-line refactoring change drops our ultra-expensive SLOAD operations from 3 down to just 1. By caching the variable, we substitute those heavy 800 gas storage reads with incredibly cheap stack or MLOAD operations. If you pull up the compiler's EVM assembly output, you literally see those extra SLOAD lines just disappear. When you actually measure the gas delta, it's a massive, immediate win for your contract.
Moving into the home stretch with Section 5, the optimization loop. Let's look at the diagnostic procedure.
You really need to establish this rhythm in your daily coding life. Step 1. Produce deterministic opcodes. Keep your compiler version and optimizer settings strictly locked in so you always have a reliable baseline. Step 2. Identify the dominant cost. Comb through and look for those heavy hitters like SLOAD and SSTORE. Step 3. Refactor the code based directly on that specific evidence. And finally, Step 4. Measure the actual gas delta using a gas reporter and meticulously document the difference to prove your fix actually worked.
Remember this golden rule. When you are optimizing, targeting dominant opcodes gives you way more mileage than endlessly tweaking logic that doesn't interact with storage. Seriously, eliminating just one dominant STORE, say by batching your loop writes into memory and then writing to storage just once at the very end, will absolutely beat doing 100 micro-optimizations swapping out tiny push opcodes. Always go for the biggest leaks first. I absolutely love this quote from our course materials. That discipline turns optimization from guesswork into reproducible engineering. Hit the nail on the head, right? By making small, incremental changes, documenting your opcode differences, and logging the exact gas changes, you transition from being just a tinkerer to a true EVM engineer. Your optimization choices become fully auditable and entirely reproducible.
As you move into your practical optimization drills and your capstone project for this module, I want you to actively look for these specific opcode patterns to optimize in your own smart contracts. Find those rogue storage reads and cache them. Hunt down those expensive loop rates and batch them. Apply this opcode efficiency loop hands-on and generate those gas reports to prove your success.
Well, thank you so much for visiting the garage with us today and getting your hands greasy with EVM opcodes. Make sure to visit forge.college to check out more amazing educational resources, practical drills, and full masterclasses on Web3 engineering.
Until next time, I want you to open up your previous projects, take a hard look at the compiler output, and ask yourself, what hidden gas guzzlers are lurking in your code right now? Get in there, find them, and optimize them. See you in the next explainer.